Let's start with this problem. Find the mean, median, mode, and range of the following data set. Now, the first thing that I would recommend doing is arranging the numbers in increasing order. So the lowest number is 7, and we have 2 of them. After that, the next number is 10, and then 14, 15, 23, and 32. Now, to calculate the mean, what we need to do is we need to take the sum of the sum. Let's start with this problem. Find the mean, median, mode, and range of the following data set. Now, the first thing that I would recommend doing is arranging the numbers in increasing order. So in this video, we're going to go over the standard normal distribution as well as some equations that you need to be familiar with. After that, we're going to work on some problems so you could see how to put these formulas to good use. So the normal distribution has the shape of a bell curve. It looks something like that. Now, the notation for it, perhaps you've seen this in your book, here's the random variable x. So for normal distribution, you have 2 important parameters that you need to know. That is the mean and the standard deviation represented by the symbol sigma. That kind of looks like theta, but there it is. Now the mean is right in the middle of the bell curve. And here this would be 1 standard deviation from the mean. And over here this will be about 1 standard deviation away from the mean on the left side. The z-score that corresponds to 1 standard deviation is simply 1. When x is less than the mean, the z-scores are negative. So 2 standard deviations away from the mean, z is equal to 2. On the left side, z is going to be negative 2. And let's say over here this is 3 standard deviations from the mean. So z is going to be 3. And the same is true for the other side. Now, the formula that you need in order to calculate the z-score is this. Z, that's a terrible looking z, let's do that again. The z is equal to x minus the mean divided by the standard deviation. Sometimes you may need to calculate x. And let's say over here this is 3 standard deviations from the mean. So z is going to be 3. And the same is true for the other side. Now, the formula that you need in order to calculate the z-score is this. Z, that's a terrible looking z, let's do that again. The z is equal to x minus the mean divided by the standard deviation. Sometimes you may need to calculate x. X is equal to the mean plus z times the standard deviation. So these are some formulas that you want to make sure you write down for the problems that I'm going to give you later. The probability density function for a normal distribution is this function here. F of x is equal to 1 divided by the standard deviation times the square root of 2 pi times e raised to the negative 1/2 times x minus the mean divided by the standard deviation squared. And keep in mind, e is a number. It's approximately 2.718 something. Yeah, this continues. Now, In a regular statistics class, you won't need this formula. You just need to know that it is the PDF or the probability density function for the normal distribution. But you really don't need to use it in order to calculate the answer, unless you're using it with calculus or something. It does involve integral calculus to calculate the probabilities with that formula. I've actually did that in another video on YouTube. You could find it. It was probably posted about a year ago or something, if you want to know how to use calculus to get the answer. But for this particular video, we're not going to go into that much detail. But just in case you see a question on a test, at least you know that this formula corresponds to the normal distribution. Now, there's something called the empirical rule that you need to be familiar with. So the empirical rule tells us that 68% of the x values lie within one standard deviation of the mean. 95% of the x values lie within 2 standard deviations of the mean. And 99.7% of the x values lie within 3 standard deviations of the mean. So knowing that, how would you calculate the area under the curve expressed as a percentage in each of these sections? Well, if this area here is 68%, if we divide that by 2, that means this region must be 34%, as well as the left side as well. Now, what is the area in terms of a percent for those 2 regions? To get that answer, you need to subtract these 2 numbers. 95 minus 68, that's going to give us 27. And then if you divide that by 2, you're going to get 13.5. Now, it's important to understand that the area of a continuous probability distribution function is 1. So the area of this region is going to be a decimal value. It's 0.135. The same is true for this region here. So keep that in mind. The total area under the curve is equal to 1. Now, what is the probability of finding an x value in those 2 regions? So what we need to do is subtract those 2 numbers. 99.7 minus 95, that's going to give us 4.7, and then divide that by 2. So you should get 2.35%. That's the probability of finding or getting an x value in that region. Now, the remaining portions, by the way, this should be like very close to the x-axis. My drawing wasn't perfect. But to find the remaining part, it's going to be 100 minus 99.7, which is 0.3, divide that by 2. And so there's a 0.15% chance of finding of getting an x value beyond 3 standard deviations. So those are the values when using the empirical rule to solve probability questions relating to the normal distribution. We're going to talk about how to use this chart later in this video. But feel free to write down this information because it's going to be useful shortly. So here's the first example problem that we're going to work on in this video. Now for each of these problems, feel free to pause the video if you want to try it yourself before seeing the answer. And when you want to check your answer, just play the video to see if you got it. So let's begin. So given this information here, what are the values of the mean and standard deviation? So what you need to know is that the first number corresponds to the mean, the second number corresponds to the standard deviation. So the mean is 50 in this example, and the standard deviation is 10. Now part B, what value of x has a z-score of 1.4? So if z is equal to 1.4, what is the value of x? What do you think we need to do? What formula should we use? So perhaps you wrote down this formula. X is equal to the mean plus z times the standard deviation. So the mean is 50, the z-score is 1.4, and the standard deviation is 10. Now 1.4 times 10 is 14, and 50 plus 14, that's going to give us 64. So this is the answer for part B. So that's how you can calculate x of that form. Now let's move on to part D. What is the difference between positive and negative z-values? Let's create a number line, and let's put the mean in the middle. Now, when x was 64, this corresponded to a z-value of positive 1.4. And when x was 30, the z-value that it corresponded to was negative 2. So as you can see, negative z-values are below the mean. They correspond to x values that are below the mean. And positive z-values correspond to x values that are above the mean. And so that's really the difference between positive and negative z-values. The negative z-values are going to be to the left of the mean, and the positive z-values will be towards the right of the mean. Now, let's move on. Are going to be to the now, part value, there's a 0.15% chance to solve probability questions relating to the normal distribution. We're going to talk about how to use this chart later in this video. But feel free to write down this information because it's going to be useful shortly. So here's the first example problem that we're going to work on in this video. Now for each of these problems, feel free to pause the video if you want to try it yourself before seeing the answer. And when you want to check your answer, just play the video to see if you got it. So let's begin. So given this information here, what are the values of the mean and standard deviation? So what you need to know is that the first number corresponds to the mean, the second number corresponds to the standard deviation. So the mean is 50 in this example, and the standard deviation is 10. Now part B, what value of x has a z-score of 1.4? So if z is equal to 1.4, what is the value of x? So now they are above the mean. Now this is going to be one step I need to be helpful. Okay, maybe I need to draw a better picture. Let's say that's our bell curve. And in the middle somewhere is the mean. The mean is 74. Now this is going to be one standard deviation away from the mean, which is 8. So if we add 74 and 8, this will give us 82. 2 standard deviations away from the mean will be 90. And 3 standard deviations will be 98. Now we're going to do the same for the other side. 74 minus 8 will give us 66. 66 minus 8, that's going to give us 58. And then subtract that by 8 again, you should get 50. So now I'm going to fill in the values that we had before. So we know that this is 34%. So the area under the curve for this region is 0.34. So keep that in mind. To do is just add 0.15% values, because selecting a student who scored a 58. And that's going to give us 2.5%. Selected 2 numbers. And so it's 30 plus 60 and 2 parts student. So in this region, everything below 90 plus 30. So the scored, the probability, and the calculation for this will be easier. Now, of those values as percent, 97 ask us how many students scored at most 90. So we're looking for the number of students. Divide the answer from part C. Point in this class. So we need to determine 90 inch for our answer. Because part C, it asks us how many students scored at most 90. So we're looking for the number of students. And there are 2,000 students in this class. So we need to determine what is 97.5% of 2,000. 97, so percentage of students greater than or equal to 66. So therefore we need everything to the right of 66. Answer, part E, how many students scored more than 98 on the test? So that's how you situation. Now, whenever you have z-scores like 1, 2, 3, or -2, -1, you could use the empirical rule to calculate the area under the curve. Just calculating. You have probability problems related to a normal distribution situation. Now, sometimes you have z-scores that are not whole numbers of the standard deviation, and you can't use the empirical rule. Whenever you have z-scores like 1, 2, 3, or -2, -1, you could use the empirical rule to calculate the area under the curve, just calculating the probability in question. But let's say if your z-score is 1.56, you can't use the empirical rule to calculate the area under the curve. And if you don't want to use integral calculus, you need to use the standard z-tables, sometimes referred to as the normal distribution tables. Now I'm going to show you how to use it real quick, but let me talk about the graph. So here is our standard normal distribution. Let's say this is the mean. And let's say this is the z-score of 1.56. So when you get the area under the curve from the z-table, which for this problem, it's going to be 0.94062, you need to understand that this gives you the area to the left of that line. Let me put this line in red. So it gives you the left side, the area of the shaded region in blue. Let's say if your z-score is negative, let's say z is negative 0.43. Using the table, you'll find that the area to the left is 0.33360. And so the graph, if you wish to shade the region, will look something like this. Here's the mean. Z is negative, so it's going to be to the left of the mean. So it's going to be to the left of the dotted line. So that shaded region corresponds to an area of 0.3336, which means if you want to convert that to a percentage, the probability that x lies in this region somewhere will be 33.36%. You just need to multiply that by 100. So here we have a positive z-score table. So the first thing we're going to do is look at the first column and find a value that corresponds to 1.5. Now looking at the first row, we need to find a value that corresponds to 0.06, because 1.5 plus 0.06 gives us the z-score that we want, 1.56. Now we need to find the number that corresponds to the row 1.5 and the column 0.06. And as you can see, that number is 0.94062. So that represents the area under the curve, given a z-value of 1.56. So the area of the blue region shaded to the left, the area under the curve, that's going to be 9.94062. So that's how you can find it using the positive z-score table. Now the next z-score value that we're looking for is negative 0.43. So in the first column, we see the value negative 0.4, and in the first row, we need to look for the column that says 0.03. So the value that corresponds to a z-value of negative 0.43 is 0.33360. That is going to be the area under the curve, given a z-value of negative 0.43. So that's how you can find the area under the curve if you know the z-score. You just got to look it up in the table, and you'll get the answer. Number 3, normally distributed IQ scores have a mean of 100 and a standard deviation of 15. Use the standard z-table to answer the following questions. What is the probability of randomly selecting someone with an IQ score that is less than 80? So let's write down what we know. The mean is 100, and the standard deviation is 50. Questions. Have a mean of 100 and a standard deviation of 15. Use the standard z-table to answer the following questions. What is the probability of randomly selecting someone with an IQ score that is less than 80? So let's write down what we know. The mean is 100, and the standard deviation is 15. Now let's draw a picture. So here is a rough sketch of our bell curve. The mean is 100, and we want to find the probability of selecting someone with a score of less than 80. So what we need is the area to the left of 80. So the first thing we need to do is calculate the z-score, and then we could use the z-table to get the area under the curve. So we know that z is going to be x minus the mean divided by the standard deviation. So x is 80, based on this problem. We're trying to find the probability that x is less than 80. So we're going to say x is 80. The mean is 100, and the standard deviation is 15. So 80 minus 100 is negative 20. Negative 20 divided by 15 is negative 1.33. Now it's negative 1.3 repeated, but we're going to stop it at negative 1.33. So what you need to do at this point is use the negative z-table and find the area, the value of the area that corresponds to the z-value. So using that table, you should get 0.09176. Now that's the answer as a decimal. If we multiply this by 100, we'll get the answer as a percentage, which is 9.176%. So that is the probability of selecting someone with an IQ score less than 80. Now let's move on to part B. What is the probability of randomly selecting someone with an IQ score that is greater than 136? Go ahead and try that. So first, let's begin by calculating the z-score. It's going to be x minus the mean over the standard deviation. So that's 136 minus 100 divided by 15. So 136 minus 100 is 36, and 36 divided by 15 is 2.4. So using the positive z-score table, convert the z value of 2.4 to the area value. So find the area under the curve that corresponds to a z-score of 2.4. Go ahead and take a minute to do that. Want to write x1 minus this, that x is between 95 and 110. In order to do that, in order to calculate the probability that x is between 95 and 110, we need to take the difference of the probability that x is less than 110 and the probability that x is less than 95. The probability that x is less than 110 looks like this. But we need to calculate the z-scores that correspond. So let it by now by 15 to a z corresponds to 7. So let's 0.3 is not now percentile. We have drawn many pictures in this video so far. So here's the mean. The mean is at the 50th percentile. This is 0, this is 100. So the 90th percentile would be somewhere in that area approximately. And there is an x value that corresponds to the 90th percentile. We need to determine what that x value is. Now what we know is that the area to the left of that x value is based on the percentile. If the percentile is 90, the area to the left has to correspond to 0.90. And so using the z-table, we can kind of work backwards in reverse here. We can take that area and find the z-score that corresponds to it. So find the z-score that corresponds to an area of 0.90. We need to use the positive z-table because the area is greater than 0.5. Now there's two values of interest. A z-score of positive 1.28 has an area of 0.89973. And a z-score of 1.29 has an area to the left of 0.90147. Now this value is a lot closer to 0.9 than is this value. It's about 5 times as close. If you take the difference between this number and 0.9, you can see that it's a lot smaller than the difference between this number and 0.9. So I'm going to choose a z-score of 1.28. So now that I have the z-score that corresponds to the 90th percentile, I can calculate the x value using this formula. X is going to be the mean plus z times the standard deviation. So the mean is 100, the z is 1.28, and the standard deviation is 15. So go ahead and type that in. The answer that you should have is 119.2. So this is the IQ score that corresponds to the 90th percentile. Part E. The middle 30% of IQs fall between what two values? So what do you think we need to do to get that answer? Part E is very similar to Part D. Let me show you why. So let's put the mean here. So this is going to be 100. And we're going to call this value x2 and this one x1. Those are going to be the two IQ values that we're looking for. Now granted, it's not drawn to scale. So this is going to be the middle 30%, which means that 15% will be on the right side and 15% will be on the left side. So we need to we need to find the x values that correspond to these percentages. Now understand that this is the 50th percentile. So 15% to the right of that will bring us to the 65th percentile. And 50 minus 15 on the left will give us the 35th percentile. So we need to find the x value that corresponds to the 35th percentile, and the x value that corresponds to the 65th percentile. So that's how it's similar to part D. So let's start with the 65th percentile. That means the area to the left, that is everything from here, if you find the area under the curve, all of this will have an area of 0.65. So now, using the positive z-table, what z-score corresponds to an area of 0.65? So now, using the positive z-table, area of 0.65. Thing from here, if you find the area under the curve, all of this will have an area of 0.65. So now, using the positive z-table, what z-score corresponds to an area of 0.65? What would you say? Now, there's two values of interest. When z is 0.38, the area is 0.64803. It's pretty close to 0.65. And when z, so these two values, the average, 5 is in the middle. 5, it's going to be q. So think collective based on the standard normal distribution. So that's it for number 3. Now let's move on to number 4. Company XYZ manufactures an average of 400,000 tires annually. On average, 2% of the tires were manufactured with a defect. A random sample of 500 tires were selected for quality control. Part A, calculate the mean and standard deviation of the defective tires in the sample. So take a minute. To work on this problem. The first thing that we want to take into account is that 2% of the tires have a defect. So the probability of getting a tire with a defect is 0.02. The probability of not getting a tire with a defect, that's going to be Q. That's 1 minus 0.02, which is 0.98. Now, we're choosing a sample size of 500 tires, so N is 500. So we're choosing a small sample out of the 400,000 tires that are manufactured annually. Now, to calculate the mean in this situation, we could use this formula. It's going to be N times P. So it's 500 times 0.02. So basically, we're looking for 2% of 500. 0.02 times 500 is 10. So about 10 of the 500 tires on average will have a defect. So that is the mean. Now, let's calculate the standard deviation. The formula that we're going to use is this one. It's the square root of N times P times Q. So N is 500, P is 0.02, and then Q is 0.98. So this is going to be 3.13. So that is the standard deviation in this problem. So that's it for part A. Now, part B, what is the probability that less than 8 tires will be defective in the sample? First, let's rewrite the mean and the standard deviation so I can create more available space. So we need to use the z-table, but first we need to calculate the z-score. So z deviation, 6.1% approximately. That's a rounded answer. Move on to part 1.c. That's point. So let's move on. It's going to be the probability that occurs. In this video, we're going to talk about the law of large numbers. So what is the law of large numbers? Well, let's say if you perform an experiment multiple times, the observed average of the results will approach the true average or the theoretical average as you increase the number of trials. So let's use an example to explain this concept. Let's say if you have a coin. If you flip a coin, there's only two possibilities. You either get heads or you get tails. The probability of getting heads when you flip a coin, it's 1 out of 2 because there's two possibilities. Only one outcome is a favorable outcome. So it's 1 out of 2 or 0.5, which means there's a 50% chance that you'll get heads. Now, let's say if you flip 10 coins. Now, keep in mind, this is the theoretical probability of getting heads. But let's say if you flip 10 coins, will you get 5 heads? Because that's 50% of 10. You may get 5 heads or you may not. You might get 4 heads and 6 tails. Thus, your observed probability in this case is 4 out of 10, or 40%. Now, let's increase the number of coins. So let's say if we flip it 50 times. Now, we may not get 25 heads. Instead, we might get, let's say, 26 heads and 24 tails. I forgot to put the H. But if we get 26 heads and 24 tails after, let's say, throwing 50 coins in the air, the probability in this case will be 26 out of 50. We got 26 successful events out of 50 coin choices. So the probability now is 0.52. So let's increase it. Let's say if we toss 100 coins in the air, we might get 49 heads and 51 tails. In this case, it's going to be 49 over 100 or 0.4. Now, let's say if we did it 1,000 times, if we threw 1,000 coins in the air. In this case, we might get 497 heads and maybe 503 tails. So the probability will be 497 divided by 1,000. And so that's going to be 0.497. So notice that this number is very close to 0.5. So the more coins that you toss in the air, the probability will get closer and closer to 0.5. And so as the number of trials increases, the observed probability approaches the theoretical probability. And that's the basic idea behind the law of large numbers. Now let's use another example to illustrate this concept. Let's say you wish to measure the average weight of everyone in a town. And let's say there's 20,000 people living in town XYZ. Now you don't want to measure the weight of all the individuals living in this town because that's going to be a lot of work. But let's say if you take a sample. Let's say if you take a sample of 5 individuals. The average weight may be 160 pounds. Let's say if you take 10 individuals and you measure their weight, the average weight might be 154 or something. Now let's say if you measure the weight of 50 individuals, that number's going to change. It might be 163. And let's say if you measure the weight of 100, that might be 161. But eventually, as your sample size increases, these values will converge. Let's say if you measure 200 individuals, it might be 162. Or let's say if you measure the weight of 500, it might be 161.5. And so notice the value we're getting closer to. We can see that the average weight of the individuals in this town is somewhere around 161, 162. If we measure 1,000 individuals, which will take a lot of work, we might find that the average is 161.8. So we can say that the average weight of people in this town is somewhere between 161 and 162 because as n became very large, we see that the average is convergent to this value. If we were to select just one individual, we might get an extreme value. We may get someone who is overweight, maybe like 230 pounds, or we may get someone who's underweight, which may be like 10 pounds. So you might get an extreme value if you just select one person, but as the number of individuals that you select in your sample increases, then the average will approximate the true average of the entire population. And so that's another example of how the law of large numbers can be used to estimate parameters of the population using samples. In this video, we're going to talk about the central limit theorem. So what is the central limit theorem? The basic idea behind the central limit theorem is this. Let's say we collect samples of size n from a population, and then we calculate the mean of each of those samples, and then plot those means on a histogram. The histogram will approximate a normal distribution. So imagine if is the central limit theorem. In this video, we're going to talk about the central limit theorem. So what is the central limit theorem? The basic idea behind the central limit theorem is this. Let's say we collect samples of size n from a population, and then we calculate the mean of each of those samples, and then plot those means on a histogram. The histogram will approximate a normal distribution. So imagine if, let's say you have 100,000 people in a town, and you choose a sample of 30 individuals, and then you calculate, let's say, the mean of sample 1. Let's say you calculate the mean age of the 30 individuals in the sample. Let's say it's 41.8. And then you calculate the mean of another set of 30 individuals. Let's say it's 39.6. And then you take another sample of 30 people. You calculate their mean age. Let's say it's 40.5. And then you repeat this process. And then if you take all of these means and plot it on a graph, the graph will have the shape of a normal distribution. Even if the graph of the population, which we don't know, even if it's not normal shape, and then the mean of the 30 individuals in the sample, let's say it's 41.8. And then you calculate the mean of another set of 30 individuals. Let's say it's 39.6. And then you take another sample of 30 people. You calculate their mean age. Let's say it's 40.5. And then you repeat this process. And then if you take all of these means and plot it on a graph, the graph will have the shape of a normal distribution. Even if the graph of the population, which we don't know, even if it's not normal, this graph, where we plot all of the sample means, or the means of each sample, so this will be x bar, it will have the shape of a normal distribution. So that's the gist of, or the means of each sample, so this will be x bar. This graph, where we plot all of the sample means, or the means of each sample, so this will be x bar, it will have the shape of a normal distribution. So that's the gist of the central limit theorem. If the sample size is large enough, the sample distribution taken from any population distribution, regardless of its shape, will approximate a normal distribution. A good value is if n is equal to or greater than 30. So let me illustrate that with some examples. So on the left, I'm going to put the population distribution. And on the right, I'm going to draw the shape of the sampling distribution. So for our first example, let's say that the population distribution has the shape of a normal distribution with mean mu and a random variable x. Now, if we collect samples out of this population and calculate the means of those samples and then plot it on a graph, we're going to create a new distribution called the sampling distribution, but specifically the sampling distribution. Examples. So on the left, I'm going to put the population distribution. And on the right, I'm going to draw the shape of the sampling distribution. So for our first example, let's say that the population distribution has the shape of a normal distribution with mean mu and a random variable x. Now, if we collect samples out of this population and calculate the means of those samples and then plot it on a graph, we're going to create a new distribution called the sampling distribution, but specifically the sampling distribution of the sample means, because we calculated the mean of each sample taken from the population. So this is going to be x bar, because we're plotting the means of each sample on this graph. X represents the individual observation of the population. X bar represents the mean of a sample collected from the population. So make sure you understand the difference. difference between the two on this graph. X represents the individual observation of the population. X bar represents the mean of a sample collected from the population. So make sure you understand the difference between the two. So since the population distribution had the shape of a normal distribution, the sampling distribution will also have the same shape, but for this case, for any n value. The reason why it's for any n value is because the population distribution already has the shape of a normal distribution. But now, what if the population distribution had a different shape? Let's say if it had the shape of a uniform distribution, or if it had the shape of an exponential distribution, or if it had the shape of just some unusual distribution. If we collect samples from the population, calculate the mean of those samples, and plot it on a graph, we're going to have the sampling distribution of the sample means. And if n is large enough, if n, let's say it's greater than or equal to 30, then the sampling distribution will approximate a normal distribution. So in this case, if the population distribution has a shape other than a normal distribution, you need to collect samples with a large enough size, 30 or more. Now, for those of you who are wondering what a sampling distribution of the sample means is, it's simply a probability distribution where the sample mean is plotted on the x-axis. Now, since the sampling distribution approximates the shape of a normal distribution, wondering what a sampling distribution of the sample means is, it's simply a probability distribution where the sample mean is plotted on the x-axis. Now, since the sampling distribution approximates the shape of a normal distribution according to the central limit theorem, we could use the z-table to make some probability calculations. So let's say if we wish to calculate the probability that a sample taken from the population is somewhere between A and B on this graph, we could use the z-tables to get the area under the curve, and thus the probability that the sample mean is between A and B. Now let's talk about some symbols and variables that you need to know. So mu, this is the population mean. You've seen that before. The next one is x bar. This is the mean of the sample, or you could say the sample mean for short. Next, we have mu with a subscript x bar. So this is the mean of the sampling distribution. Next is sigma. This is the standard deviation of the population. S represents the standard deviation of the sampling. I take that back. It's the standard deviation of the sample, not the sampling distribution. Sigma with an x bar as a subscript, that is the standard deviation of the sampling distribution. So notice the difference between S and sigma sub x bar. S is just the standard deviation of a single sample. Sigma sub x bar, that's the standard deviation of many samples, of a sampling distribution. So here you have just one sample, and here you have many samples, an infinite number of samples. So notice the difference. Lastly is n. N is just the size of the sample. Now the next topic that we need to talk about is the law of large numbers. And the basic idea behind the law of large numbers is that, in reference to the topic that we're talking about, let's say we take a sample. If we increase the size of that sample, the mean of the sample will get closer and closer to the mean of the population as n increases. So let's say if the average age in a certain town is 36, so that's the population mean. But now let's say there's 100,000 people in that town. In order to get this answer, you don't want to calculate you don't want to ask 100,000 people, hey, what's your age, to calculate this number. Instead, what you want to do is you want to take small samples and calculate the mean of those samples to estimate this number. So let's say the first sample that you take has, let's say, 10 individuals, and you calculate the mean or the average age of those 10 individuals. Let's say you get 32. The next sample, let's say you ask 50 people for their age, and you calculate the mean of that sample. Let's call this sample 2. Let's say you get 38.5 as the average age. Next, let's say in your third sample, you average the ages of 100 individuals. Your answer will get closer to the true answer. So let's say this one will be 35.3. And then finally, you throw the long ball, ask 1,000 people, and you get a mean of 36.1. Notice that as n increases, x bar gets closer and closer to the actual mean of the population. And that's the basic idea behind the law of large numbers. Because if you have a small sample, an extreme or an outlier may greatly affect your mean. So if you ask one person who's like 100 years old, this will greatly affect the average. Or if you ask a baby who's like less than 1 year old, it's going to affect the average big time. But the basic idea behind the law of large numbers is that as n goes up, the mean of the sample gets closer and closer to the population mean. Now let's think about this. If the mean of one sample can approximate the population mean if that sample is large enough, what about many samples? If it's up, the mean of the sample gets closer and closer to the population mean. Now let's think about this. If the mean of one sample can approximate the population mean if that sample is large enough, what about many samples? As n goes up, the mean of the sample gets closer and closer to the population mean. Now let's think about this. If the mean of one sample can approximate the population mean if that sample is large enough, what about many samples? Well, the same will be true according to the law of large numbers. As n increases, the mean of the sampling distribution will approximate or get very close to the population mean. So if n is large enough, let's say if n is 30 or more, the mean of the sampling distribution is basically equal, you can say approximately equal to the population mean. Now, this is important to note because when we need to calculate z, this will affect the equation. No, because an extreme or an outlier may greatly affect your mean. So if you ask one person who's like 100 years old, this will greatly affect the average. Or if you ask a baby who's like less than 1 year old, it's going to affect the average big time. But the basic idea behind the law of large numbers is that as n goes up, the mean of the sample gets closer and closer to the population mean. Now let's think about this. If the mean of one sample can approximate the population mean if that sample is large enough, what about many samples? Well, the same will be true according to the law of large numbers. As n increases, the mean of the sampling distribution will approximate or get very close to the population mean. So if n is large enough, let's say if n is 30 or more, the mean of the sampling distribution is basically equal, you can say approximately equal to the population mean. Now, this is important to note because when we need to calculate z, this will affect the equation. You've seen this equation for a normal distribution. Z is equal to the random variable x minus the population mean divided by the population standard deviation. In the case of a sampling distribution, z is going to be x bar minus the mean of the sampling distribution divided by the standard deviation of the sampling distribution. Now, the standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of n. And when n is large in distribution, standard deviation, this will affect the equation. You've seen this equation for a normal distribution. Z is equal to the random variable x minus the population mean divided by the population standard deviation. In the case of a sampling distribution, z is going to be x bar minus the mean of the sampling distribution divided by the standard deviation of the sampling distribution. Now, the standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of n. And when n is large, we can replace the mean of the sampling distribution with the mean of the population. So we get this equation. We can calculate z using this formula, x bar minus the population mean divided by the population standard deviation over the square root of n. So if n is large enough, when the sampling distribution approximates a normal distribution, you can do your probability calculations using this formula. formula by calculating z and then using the z tables. Now let's talk about the effect that the size of the sample has on the shape of the sampling distribution. So here's a question for you. If we increase the size of the sample, what effect does it have on the standard deviation of the sampling distribution? Will it go up or down? Now we said that this. So here's a question for you. If we increase the size of the sample, what effect does it have on the standard deviation of the sampling distribution? Will it go up or down? Now we said that the standard deviation, I need to make sure I'm writing sigma instead of theta. We said that the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of n. Now notice that n is in the denominator of this fraction. Whenever you increase the value of the denominator, the value of the fraction goes down. So what we have here is an inverse relationship. By the way, the standard deviation of the sample means, or the standard deviation of the sample distribution, is also called the standard error. So notice that as n increases, the standard error decreases. So if the error is less, the accuracy is better. What this means is that the shape of the graph becomes more narrow. The data will be just that with inverse relationship. By the way, the standard deviation of the sample means, or the standard deviation of the sample distribution, is also called the standard error. So notice that as n increases, the standard error decreases. So if the error is less, the accuracy is better. What this means is that the shape of the graph becomes more narrow. The data will be less spread in the sampling distribution. So let's say if n is 10, the sampling distribution will have a very wide shape. It may look something like this. It's going to be short and wide. Let's say if n is 30, it's going to be taller and more narrow. If n is 50, it's going to be even taller and even more narrow. So this has the longest spread and therefore the greatest error. And this one has the shortest spread and therefore the lowest error. So the standard error, or the standard deviation of the sample mean, is going to be the lowest when n is the greatest. So just keep that in mind. As the sample size increases, the standard deviation of the sample means will decrease, causing the graph to have a more narrow and taller shape. Now, before we go over some practice problems, it might be good to review some formulas that you need to know in order to solve these practice problems. So first, let's do a brief review of the uniform distribution. If you recall, the uniform distribution has a shape that looks like this. The height of the rectangle is basically f of x. F of x is a constant value. F of x is the probability density function, and in this case, it's equal to 1 over b minus a. X is restricted between a and b. The distribution can be written this way. We have the random variable x, and we have a uniform distribution, which varies from a to b. A is the minimum value, b is the maximum value. The mean of the uniform distribution is the average of a and b. So it's the sum of a and b divided by 2. The standard deviation is the difference between b and a divided by the square root of 12. So when dealing with any problem involving the uniform distribution, these are some formulas that you need to know. And keep in mind, the probability is equal to the area under the curve. So the area is a rectangle. The area of the rectangle is equal to the length times the width, or you could say the base times the height. So let's say if you want to calculate the probability that x is between c and d. The base of that rectangle is b. So that's the difference between d and c. The height is simply f of x. So the area of that region is going to be the base, which is d minus c. So the exponential distribution, those are some things that you need to know when dealing with the uniform distribution. Now let's move on to the exponential distribution. Let's spend a few minutes reviewing the formulas associated with this. So the exponential distribution has a graph that starts at the y-intercept. The y-intercept is basically the maximum value on the y-axis. And at that point, that's equal to lambda, which is the rate parameter. The function f of x is the probability density function, and it's equal to lambda e raised to the negative lambda times x. Lambda, the rate parameter, is 1 divided by the mean. And the mean is equal to the standard deviation for an exponential distribution. Now let's say if we want to calculate the performance 1 divided by the mean, and the mean is equal to the standard deviation for an exponential distribution. Now let's say if we want to calculate the probability that x is less than a. So this is equal to the area of the shaded region on the left. The area to the left is also known as, the formula that gives you the area to the left is known as the CDF, the cumulative distribution function. And in this case, you could use this formula to get it. The probability that x is less than x, in this case, that would be x is less than a. This is equal to 1 minus e raised to the negative lambda times x. If you wish to calculate the area to the right, which will be the probability that x is greater than x, this is going to be e to the negative lambda times x. Now let's say if you want to calculate the probability that x is between b and c. In this case, you need to use this expression. The probability that x is between b and c is simply the difference of the probability that x is less than c, but minus the probability that x is less than b. Now let's go over some formulas that you need to know when dealing with the normal distribution and the sampling distribution. Probability that x is between b and c. In this case, you need to use this expression. The probability that x is between b and c is simply the difference of the probability that x is less than c, but minus the probability that x is less than b. Now let's go over some formulas that you need to know when dealing with the normal distribution and the sampling distribution. I'm going to put these two together so you could compare and see the difference. So here's the typical shape of the normal distribution. It has the population mean mu and the random variable x. The sampling distribution, if n is large enough, will have the same shape approximately, but with the standard deviation of the sample means. That's mu x bar. And on the x-axis, instead of x, it's going to be x bar, the means of each sample. Now to write the distribution, for normal distribution, we have the random variable x, n for normal distribution, population mean mu, and the standard deviation sigma. Now for the sampling distribution, we can write it this way. Instead of x, it's going to be x bar. It's still the shape of a normal distribution with the mean mu. Now keep in mind, when n is large enough, these two are approximately the same. So you can just write mu instead of mu x bar. So the mean is going to be the same, mu. And then this is going to be, now, so the standard deviation of the sample distribution is sigma divided by the square root of n. So we're not going to have sigma here, but we're going to have sigma over the square root of n in this area. So notice the difference. X bar instead of x, and then sigma over square root n divided by, instead of just sigma. Now let's say if we want to calculate the probability that x is less than a. To do that, we need to calculate the probability that z is less than x minus mu over the standard deviation if we have a normal distribution. Now for a sampling distribution, let's say we want to do the same thing. The probability that x is less than a for the sampling distribution is going to be the probability that z is less than x bar, the sample mean, minus mu, the population mean, divided by sigma over the square root of n. So when calculating the z-score for a normal distribution, you could use this formula. And when calculating the z-score when dealing with a sampling distribution, where you have a sample of size n, where n is not 1, you would use that formula to calculate the z-score, and then use the z-table to get the area under the curve, which will give you the probability. So those are the formulas that you'll need for the problems that are coming up soon. So here is the first problem. Number 1. The entrance exam scores of a certain university has a mean of 74 and a standard deviation of 6.8. The exam scores follow a normal distribution. Part A. If a student is selected at random, what is the probability that his exam score is less? The exam scores follow a normal distribution. Number 1. The entrance exam scores of a certain university has a mean of 74 and a standard deviation of 6.8. The exam scores follow a normal distribution. Part A. If a student is selected at random, what is the probability that his exam score is less than 65? So let's write down what we know. We know the mean is 74. The standard deviation is 6.8. And we're dealing with just one student, so n is 1. Now, if we were to draw a graph, we're dealing with a probability distribution that has the shape of a normal distribution. So this is going to be x instead of x bar with the mean mu. Now, we want to calculate the probability that his exam scores is less than 65. 65 is going to be to the left of the mean. So we need to calculate the area under the curve to the left of 65. So the probability that x is less than 65 is going to be, now we need to calculate the z-score. So we're going to use this formula. Z of negative 1.32 corresponds to an area of 0.09342. So what this means is that there is a 9.342% chance that if we select a student at random, that's going to be the probability that his score is less than 65. So this is the answer in the form of a percentage. To get that number, just keep in mind, you need to multiply this by 100. Now, in the 9 point gives us negative 1.32. So now that we have the z-score, let's go to the negative z table to get the answer. So a z-value of negative 1.32 corresponds to an area of 0.09342. So what this means is that there is a 9.342% chance that if we select a student at random, that's going to be the probability that his score is less than 65. So this is the answer in the form of a percentage. To get that number, just keep in mind, you need to multiply this by 100. Now let's move on to part B. By the way, for each of these problems, feel free to pause the video and try it yourself. If a sample of 50 students is selected at random, what is the probability that the mean exam score of this group is greater than 75? Go ahead and try it. So this time n is not 1, but 50. So we're no longer dealing with a population distribution, but we're dealing with a sampling distribution. So we have x bar as the random variable instead of x. And the mean is going to be mu x bar. But the mean is still going to be 74. That's not going to change. So what do we need to do here? Well, first, we need to calculate the probability that the mean is greater than 75. So 75 is somewhere to the right of 74. And we're trying to calculate the area of the shaded region. So once again, we need to calculate z. When dealing with a sampling distribution, z is going to be x bar minus mu. If n is small, it's going to be mu x bar. But since n is large, mu x bar is the same as mu. So just keep that in mind. And then divided by the standard deviation over the square root of n. So this is going to be, well, first, to get the probability or the area to the right, it's going to be 1 minus the probability that x bar is less than 75. Because the z table, it gives us the area to the left. So we have to find the complement of that value. So now let's use this formula to get the z-score. So this is going to be 1 minus the probability that z is less than x bar being 75, minus the mean, mu, which is 74, over the standard deviation, which is 6.8, divided by the square root of n, and n is 50. So 75 minus 74, that's going to be 1. And 6.8 divided by the square root of 50, that's 0.961665. So 1 divided by that number is approximately 1.04 if you round it. So now we can go to the positive z table to get the area corresponding to this value. So this is going to be 1 minus. Now a z-score of 1.04 corresponds to an area. This is an area to the left, that's this region, of 0.85083. So just keep in mind this value corresponds to the shaded region in red. But when we use that number and subtract it from 1, we're going to get the area in blue, which is what we want. So the final answer is 0.14917. So what this means is that there's a 14.9% chance that if we select a sample of 50 students, the mean exam score is going to be greater than 75. Now let's move on to part C. What is the distribution for the mean exam score of 50 students? How can we write the distribution for the mean exam score? So because we're dealing with the mean, it's going to be x bar. And it is a normal distribution. And then we need to write the mean. And we also need to write the standard error, which is going to be sigma divided by the square root of n. So now, let's replace the mean, it's the mean of the sampling distribution, which is still going to be 74. And then sigma over square root of n, that's 6.8 divided by the square root of 50. And that is going to be 0.9617 if you round it. So that's how we can write the distribution for the mean exam scores of 50 students. Now let's move on to part D. Find the 80th percentile for the mean exam score of the 50 students. So going back to our normal distribution, we have a mean of 74. And at the bottom, towards the left, this is the 0th percentile. The middle is the 50th percentile. At the end, that's the 100th percentile. So somewhere to the right of 74 is the 80th percentile. We need to calculate the mean score that corresponds to the 80th percentile. Now, when dealing with the 80th percentile, the area to the left is going to be 0.80. So what we need to do is we need to use that to calculate the z-score. Because once we have the z-score, we could use this formula to calculate x bar. It's going to be, x bar is going to be the mean plus z times the standard error. So using the positive z-score table, an area of 0.8 corresponds to a z-score of 0.84. The actual area is like 0.79955, but that's the closest we can get to 0.8. So this is our z value, and we're going to plug it into this equation. And so the mean is 74. The z value is 0.80. Z 9 grams. The amount of carbs found in a snack bar produced by company XYZ follows a uniform distribution with a minimum of 21 grams to a maximum of 29 grams. A sample of 100 snack bars is taken for analysis. Part A. Write the distribution for the amount of carbs found in one snack bar and calculate the mean and standard deviation. So here's a question for you. For part A, are we dealing with a population distribution or a sampling distribution? Well, we're dealing with one snack bar, so we're not dealing with a sampling distribution yet. We're dealing with a population distribution. Now, the shape of that population distribution is a uniform distribution. Now, we're given the minimum and the maximum value. The minimum value is 20. 21. The maximum amount of carbs in a snack bar, that's 29. Now, to write the distribution for the amount of carbs, we could use these symbols. Since we're dealing with a population distribution, the random variable is x. It has the shape of a uniform distribution, and it varies between A and B. So for part A, we could say that the distribution is x, and then U, A to B, or 21 to 29. So that's the first part of part A. Now the second part, we need to calculate the mean and standard deviation. For a uniform distribution, the mean is simply the average of the minimum and the maximum values. So we're going to add 21 and 29, and then divide by 2. 21 plus 29 is 50. Half of 50 is 25. So the mean is 25. Now let's calculate the standard deviation. The formula that we need is b minus a divided by the square root of 12 for a uniform distribution. So that's 29 minus 21 divided by the square root of 12. 29 minus 21 is 8, and 8 divided by the square root of 12 will give us this number. So the standard deviation is 2.3094. So that's it for part A. Now, let's move on to part B. What is the distribution for the mean amount of 100 snack bars? What would you say? So now for part B, n is no longer 1. N is 100. So are we dealing with a population distribution or a sampling distribution? Since n is greater than 1, we're dealing with a sampling distribution, but a sampling distribution of the sample means. Now, what type of shape does the sampling distribution take? Would you say it has a shape of an exponential distribution, a uniform distribution, or a normal distribution? What would you say? Well, based on the central limit theorem, when n is greater than 30 or more, if n is sufficiently large enough, it doesn't matter what the shape of the population distribution is. In this case, the population distribution shape is uniform. But regardless of its shape, the sampling distribution will have the shape of a normal distribution when n is sufficiently large. So since we're dealing with a sampling distribution of the sample means, we're going to write x bar instead of x. And it takes on the shape of a normal distribution with the parameters, the mean and the standard error. So we know that the mean is 25. Now to calculate the standard error, it's going to be the standard deviation divided by the square root of n, and n is 100. The square root of 100 is 10. So 2.3094 divided by 10, that's going to be 0.23094. So that's how we can write the distribution in part B. Now let's move on to part C. What is the probability that a single snack bar has between 24 grams and 26 grams of carbs? Go ahead and try that. So we know that n is 1. So this raises a question. Are we dealing with a population distribution or a sampling distribution? Since we're analyzing a single item, we're dealing with a population distribution. And it has the shape of a uniform distribution. So let's graph it. The minimum value is 21. The maximum value is 29. Now, how can we calculate the probability that the single snack bar X is between 24 and 26? To calculate the probability when dealing with a uniform distribution, you need to calculate the area under the curve in this range. So we need to calculate the area of this rectangle. But first, we need to find the y value of that distribution, which is f of x. Now, f of x is equal to 1 over b minus a. b is 29, a is 21. So f of x, the probability density function, is 1 over 8. So now we can calculate the probability that x is between 24 and 26. This is going to be the area of the rectangle, which is the base times the height. So the base is the difference between 26 and 24, which is 2. The height is basically its f of x, which is 1 over 8. So this becomes 2 over 8. 8 divided by 2 is 4, so 2 over 8 is 1 over 4. And 1 over 4 as a decimal is 0.25. So based on the shape of the uniform distribution, the probability that a single snack bar has between 24 and 26 grams of carbs is 0.25. Now, let's move on to part D. Find a probability that the mean amount of carbs in 100 snack bars is between 24.9 grams the probability that x is between 24 and 26. This is going to be the area of the rectangle, which is the base times the height. So the base is the difference between 26 and 24, which is 2. The height is basically, it's f of x, which is 1 over 8. So this becomes 2 over 8. 8 divided by 2 is 4, so 2 over 8 is 1 over 4. And 1 over 4 as a decimal is 0.25. So based on the shape of the uniform distribution, the probability that a single snack bar has between 24 and 26 grams of carbs. So now we're dealing with the sampling distribution of the sample means, and it's going to have the shape of a normal distribution. So what we're going to is this last is going to be 200,094, 10. Get this. So this is going to be z is less than x bar, which is 25.1, minus the mean of 25, divided by. Now let's go ahead and get this value. So sigma over the square standard error minus 25. It's going to 230 the score table, the area to the left of 0.43. Now the area to the left area, the negative 0.1 divided by the same number is going to be negative 0.43. So now, using the z-score table, if you go to the positive z-score table, 0.43 gives us an area of 0.664. This is the area to the left of 0.43. Now the area to the left of negative 0.43 for z, we need to go to the negative z table. So that's going to be 0.3336. So taking the difference of these two numbers, this will give us the probability that we're looking for, which is 0.3328. So this is the answer for part D. Now, let's move on to part E. What is the distribution for the sum of carbs found in 100 snack bars? So this is another sampling distribution, but instead of dealing with the mean, we're dealing with a sum. It will still take on the shape of a normal distribution. Now the mean is going to be dealing with the sum of x, and the standard error is also dealing with the sum of x, so I changed the subscripts a bit. Now the mean value of the sum of all the carbs in 100 snack bars. If one snack bar has 25 grams of carbs, how many grams of carbs do you expect to be in 100 snack bars? It's going to be the mean times n, the sample size. So we have 25 grams in one snack bar times 100 snack bars. We should have a sum of 2,500 grams of carbs in 100 snack bars. Now to calculate the standard error associated with the sum, it's going to be the standard error that we see for the mean times n. So that's 0.23094 times 100. So the standard error in the sums is 23.094. So we can write our distribution like this. So the average sum of carbs in the 100 snack bars is 2,500 grams with a standard deviation of 23.094. Now I do need to make a correction because the sampling distribution is not associated with the mean, but rather it's associated with the sum of x. So just want to make that correction here. So this is the answer for part E. Now let's move on to part F. Find the probability that the sum of carbs, wait, what just happened there? Find the probability that the sum of carbs found in 100 snack bars is greater than 2540. So go ahead and try that. So the probability that the sum, okay, I really messed up there, that the sum of the x values is greater than with 2540, 100, sum of the x values 40. 40 divided by 23.094, this is 1.73. So using, well, first we need to get the area to the right side, which is 1 minus pz less than 1.73. That's the area to the left side. So now using the z-score table, a z-value of 1.73 corresponds to 0.95818. That's the area to the left. But to get the area to the right of 1.73, it's going to be 1 minus 0.95818. And so this gives us an answer of 0.04182. Sample of the car lasts follows an exponential distribution with a mean of 7 years. A sample of 40 40 cars is reviewed for analysis. Part A. What is the rate parameter and standard deviation? So what we know right now is that now we're going to take a sample of 4. So now we're dealing with a sample distribution. B now is the mean. So it's also equal to 7. The rate parameter lambda is 1 over the mean. So it's 1 over 7. So what we're dealing with a sample distribution, or rather a sampling distribution of the sample means. But how can we write this? An n error. Error of 1.1 bar minus the mean, the square root of n by 7 over the standard error of 1.1068. 6.5 minus 7 is negative 0.5, and if we divide that by 1, which is n. So this is the probability that z is less than x bar, which is 6.5, minus the mean of 7. Now let's go to the negative z table. Determine the I in the first quartile. Stands for the given is 7. So Q1, that percentile should be somewhere that corresponds. X bar is, let's start with plus 3 bar. X bar is equal to the mean plus the z x bar 1. The area that corresponds to the 25th percentile is 0.2. That's going to be, it's going to have a z-score of approximately negative value 5, but not exactly. Is going to be, so that basically the sample we're watching. So you can see some different, we're going to talk about, in this video, we're going to talk about how to calculate the standard error of the mean. So I'm going to give you 2 example problems so you can see some different ways on how to do it. Let's start with this one. Number one, 5 students in a college were selected at random, and their ages were found to be 18, 21, 19, 20, and 26. Part A. Calculate the standard deviation of the ages in the sample. Now, feel free to pause the video if you want to try this first. Go ahead and calculate the standard deviation, and then you can play the video to see if you have the same answer that I have. The first thing we need to do is calculate the mean, or the average, of the 5 ages that we have here. So we're going to take the sum of those 5 values. So we have 18 plus 21 plus 19 plus 20 plus 26. And now let's divide by the number of the ages that we have, which is 5. 18 plus 21 plus 19 plus 20 plus 26. That gives us a sum of 104. 104 divided by 5 is 20.8. So this is the average age of the individuals in this sample. The sample size is 5. So now let's calculate the sample standard deviation. The standard deviation of the sample is represented by the symbol S, and it's equal to the sum of all the differences between each value and the mean squared divided by n minus 1, and then the whole thing is inside of the square root symbol. So we already have the mean. X represents each of these individual values. This is going to take the whole page. So the first x value that we have is 18. We're going to subtract it from x bar, the mean, which is 20.8, and then we're going to take the square of that result. Now let's move on to the second observation that we have. The second age was 21. Subtracted from the it's negative 2 completion of the sample is 5. There's 5 ages in this sample, so we're going to divide by the square root of 5. So this is going to be 3.114 divided. This is the standard error in this example. That's how we can calculate it. In a deviation of 0.8. Part A. Calculate the standard error of the mean if a sample of 25 students were selected. Now, what type of standard deviation do we have in this problem? Because there's 2 types. There's the standard deviation of the sample and the standard deviation of the population. 0.8 is the standard deviation of all the students in this university. So that is the standard deviation of the population. and it's represented by the symbol sigma. Now, to calculate the standard error, we need to use a formula that is very similar but with different variables. The standard error of the mean is going to be the standard deviation of the population divided by the square root of n. As we said before, the standard deviation of the population is 0.8, and in part A, we chose a sample size of 25. So n is 25. Now, the square root of 25 is 5. So 0.8 divided by 5 will give us a standard error of 0.16. So that's the answer for part A. If population standard 8 divided by 10, notice that was increased. Notice that least error. So we have point to power of 2. Well, the square root of 4 is 2. You're going to get sample means, and the random variable will be x bar. So this is 2 by half. The standard error decrease by a factor of 2. So anytime you increase, if you quadruple the value of n, the standard error will decrease by half. It's an inverse relationship, and the reason being there's a square. The standard error decrease n by a factor of 4. The standard error decrease by a factor of 2. So anytime you increase, if you quadruple the value of n, the standard error will decrease by half. It's an inverse relationship, and the reason being there's a square root n on the bottom. The square root of 4 is 2. But nevertheless, though, as you increase the sample size, the standard error decreases. And so you're going to get a more accurate answer. That means the mean that you get for your sample has a higher accuracy if the standard error is less. Now, to represent this visually on a graph, let's say if we were to take many samples and calculate the mean age of the students in those samples and plot it on a graph to create a distribution. This is known as the sampling distribution of the mean. It's going to have the shape of a normal distribution. So this is the mean of the sample means, and the random variable will be x bar. Now let's say this shape corresponds to a sample size of 25. If we do the same thing, but with a sample size of 50, the graph is going to be more narrow, and it's going to be taller. So I need to redraw this one. It's going to be narrow in shape, but the height is going to be greater. So that's a visual representation that shows the effect of increasing the value of n. The standard error will decrease, creating a sampling distribution that is taller and more narrower, so there's less spread, which means the mean of the sample means will approximate the population mean more accurately. But that's it for this video. Thanks for watching. In this video, we're going to talk about how to find a confidence interval for a population mean